This is section 13.4, part C. We'll now do a few more triple integral problems, but we will only set each one up one way, the way that seems to make the most sense as we look at our object. So in example 3, we want to use a triple integral to find the volume bounded by z equals the square root of y, z equals y, x equals 0, and x equals 5. Just a reminder, this is a cylinder. That's a plane, and these are also planes. I've got this one done on Maple. We used GeoGebra last time, so just, oops, get that over there, there we go. So I did my with plots and my implicit plot 3D, and you can see I've graphed z equals the square root of y, the z equals y, and then the two planes x equals 0 and x equals 5. Z equals the square root of y is this curved part here. You can see the square root curve, and then because it's a cylinder, it's pulled parallel to the x-axis. Z equals y is this slanted line here. And so you kind of get this sort of an elongated shape in here. And then that whole elongated shape stretches between x equals 0 and x equals 5. So you sort of see the cross section there. So I'm thinking at this one, maybe it would make the most sense for us to do a dz first. What if we go from bottom to top first? And then we'll figure out what we're looking at for the y's and the z's after that. So I'm going to make a quick sketch back on my paper, best I can. There's z equals the square root of y. I'm stopping at the intersection point here. There's z equals y. And then this gets kind of pulled out along the x-axis this way, like so. All right, not a great picture, but we saw a better one in Maple. So when I'm thinking about this, I'm going to set up my limits of integration to find the volume. And I'm going to integrate the function 1, since I am doing volume. And actually, I'm kind of wondering, maybe I'm going to think about this a little differently than I originally intended to. You know, I think I'm actually going to do dx first. X clearly goes from 0 to 5. I can think of it from back to front. And I've got such a nice cross-section in the YZ plane anyway. It's easier for me to think that way. So I'm thinking back to front here. X goes from 0 to 5. That way, back here in the YZ plane, I have the region R. Again, that's z equals the square root of y, and z equals y. If I think vertical rectangles here, that would mean I'm doing the dz next. And the lower z value is just y. The upper z value is the square root of y. That leaves me to do dy last. Clearly y starts at 0, and this intersection point will tell me the y value where it ends. If I simply set y equal to the square root of y squared equals y squared minus y equals 0. I can factor that. and see that y equals 0, which I already knew, or y equals 1, which is my other intersection point. So there's my setup. Let's go ahead and do this integral. Integrating dx is just going to give me x from 0 to 5. And that's just going to give me 5 minus 0, or 5. Integrating 5 dz is going to give me 5z from y to the square root of y. So that will give me 5 square root y minus 5y. And then we can finish that last integral on the calculator, which I did and got 5/6. So that's the volume of that teeny tiny thin little slice there. All right, in example 4, we're going to look at a problem of finding the mass. We want the mass of the solid bounded by x equals 0, y equals 0, z equals 0, so all 3 coordinate planes again. Then this cylinder, y equals e to the minus z, x equals 2 and z equals 1, given this density function delta is equal to x plus 1. Our units are in grams per cubic centimeter. Let me see how much of this I can predict. Let's see, y is equal to e to the minus z. In my head, I'm kind of thinking, if I took the natural log, it'd be the negative natural log of y is equal to z, right? So, a negative ln y. That would look like this. Natural log curve, but upside down. Goes through here at 1. Z equals 1. That's just a horizontal line here. And then because the coordinate planes are all boundaries, so are the coordinate axes. So I'm thinking I'm looking at this region here. Pulled out parallel to the x-axis, since x is not mentioned here. So there, looks a little like an anvil. All right, to set up my volume, let's see, let's choose to do this one differently this time. Let's go ahead, and actually I've already drawn that, but that's okay. I think I want to go dy first this time, since I've got this equation so nicely given to me in terms of y. Oops, and I'm doing mass, not volume. So my mass, I integrate my density function, which is x plus 1, and I'd like to do the dy first. So I'm going to think from left to right. The left side is just the xz plane, so that would be y equals 0. And the right side is on this cylinder, so that would be y is equal to e to the minus z. All right, that leaves you my xz plane to contain the region R, and I need a different color because I already used my yellow this time. So in the xz plane, it looks like our region R is just going to be a rectangle. We knew that x equals 2 was a boundary, so this must be 2. And we also knew z equals 1 was a boundary, so that must be 1. And there's the region R. If I decide to go with vertical rectangles again, then I'm doing dz next from 0 to 1, and I'm doing dx last from 0 to 2. Again, there's more than one way you could have set this up. Just choosing to do the dy first this time. All right. Integrating x plus 1 dy. X plus 1 is just a constant, so it ends up getting multiplied by y. And that goes from y equals 0 to y equals e to the minus z. Plugging in the y values, I'd get x plus 1 times e to the minus z, minus just a 0. I'm going to integrate the dz next. Technically, there's like a little u substitution here. U would be minus z, but the derivative of that is just negative 1. So all that's going to do is pull out a minus sign. And then I'll get x plus 1 e to the minus z again. Integral of e to the u is e to the u. From z equals 0 to z equals 1. So I'll get x plus 1 e to the negative 1, subtract x plus 1 e to the 0. Now just remember that's not 0, that's 1, so I need that there. Just for putting in the calculator, that's like x plus 1 divided by e minus x plus 1 just times 1. And when I did that one, I ended up getting about 2.528 for the value of my integral. All right, oops, let me let that slide down. We've got one more example to do, but I think I'm going to go ahead and put that in a last video for this section.